Find the probability that a randomly selected card is both a red and a heart. I'll start with the denominator, the total number of outcomes. Well, in a random deck of cards, there's 4 suits, and each suit has 13 cards. So 4 times 13, there's 52 total cards in a deck. So that gives me my denominator because I can select any of the 52 cards. Now, how many of them fit the success requirement, which in this case is that the card is both red and a heart? Well, all the hearts are also red. So there's 13 hearts that are also red. The only other red cards are the diamonds, but those are not hearts. So any of these 13 cards is considered a success. And that can be reduced to 1/4. Part B, pick a card that is both a heart and an ace. Well, just like before, I can pick any of the 52 cards, so that's my denominator. How many of them are both a heart and an ace? Well, I only need to look at the hearts, and there's only one ace of hearts. So only 1 out of the 52 cards fits this requirement. Picking a card that is both not a heart and an ace. So I just need it to fail one of the requirements. So both not a heart and an ace. Well, there's only one card that fits both requirements. Every other card is either not a heart or not an ace. So 51 out of the 52 cards are not both a heart and an ace. So the other way we could have gotten this is the complement of, okay, so here's a full deck of cards, 52 out of 52. There's only 1 out of the 52 cards that is both a heart and an ace. So the other 51 out of the 52 cards fail the requirement. Toss a coin 4 times. What's the probability you get all 4 heads? So let's just focus on the first coin toss first. Okay, so in the first coin toss, we have 2 possible outcomes. You can either be heads or tails. So that's why the denominator is 2. And then in this case, the only successful outcome is heads. So out of the 2 outcomes, heads and tails, only heads is good. So 1 out of 2 for the first coin flip. And coin flips are independent. No matter what happened in the first one, the second one has its own, it's not reliant on the first one at all. So I ignore this for a second. Okay, so second event, again, 2 possible outcomes. Second coin can either be heads or tails, but in order to be considered a success, I need it to be heads. So only 1 outcome is good. Okay, so since these are independent events, I multiply the probabilities to see if they both happened. And I repeat for the third event. Okay, third coin flip, again, can either be heads or tails, 2 possible outcomes. And only heads is considered good. And same with the fourth event. Fourth coin flip, 2 outcomes, heads or tails, only heads is considered good. So since they're independent and I need all 4 to happen, I multiply their individual probabilities together to get a 1/6 probability of all things happening. Holly is going to draw 2 cards from a standard deck without replacement. What is the probability the first card is a king and the second card is an ace? Okay, so first, let's just focus on the initial requirement. First card is a king. So we have 52 cards total in the deck. And 1, 2, 3, 4 kings, 1 of each suit. So for her first draw, any of those 4 kings is considered a success. Okay, so once she has chosen a king, it says without replacement, so the deck changes. Instead of there being 52 cards still, let's just pretend she picked this one. Now there's 52 minus 1. Now there's 51 cards left. Okay, so our new denominator is 51 because she's already taken one card away. And the second card needs to be an ace. Okay, so she's already taken one king away, but that still leaves 4 aces left in the deck. So out of the remaining 51 cards, 4 of them are considered good for the second draw. Okay, so multiplying these together, we get 16 over 663, which is approximately 0.006. Or if we want that in percent form, that'd be about 0.6%, so less than 1% chance. Okay, Thomas has 4 blue Gatorades and 8 red Gatorades. He chooses randomly. So first, let's find the denominator, which is the number of total outcomes. Well, if he's got 4 blue Gatorades and 8 red Gatorades, he's got 12 bottles to choose from. So you can pick any one of the 12 Gatorades. So first, we want him to pick a blue Gatorade. So there's 4 blue Gatorades that are considered a success. He can pick any one of those 4. And then now he needs to pick a red one. So after he's taken away, let's pretend he's been successful. He took a blue Gatorade the first time. Now there's 3 blue Gatorades remaining, but there's still the 8 red Gatorades. So now there's only 11 Gatorade bottles, and 8 of them are red. So now any of those 8 red ones is considered a success. Okay, so multiplying these together, we get 32 over 132, which reduces to 8 over 33, approximately 0.242, or about 24.2%. Okay, during their careers, Kobe Bryant was an 84% free throw shooter, Shaquille O'Neal, 53% free throw. So what's the probability they each make one shot? Okay, so Kobe Bryant, 84%. I'll convert to decimal form, 0.84. Shaquille O'Neal, 53%. Convert that to decimal form, 0.53. And we're going to say these are independent events. Whether Kobe makes or misses doesn't affect whether Shaq makes or misses. So since they're independent events, we just multiply their probabilities. So probability Kobe makes it times probability Shaq makes it. Okay, John is playing cards. What is the probability of pulling an ace or a queen from the deck? Okay, so looking at our list of possible cards, we know there's 52 total cards to choose from, so that's our denominator. And he wants to pull either an ace or a queen. Well, there's 4 aces that would be good for him, and there's 4 queens that are also good for him. So 4 plus 4, there's 8 cards that would be good for him. And this could be reduced to 2 over 13. George is playing cards. What is the probability of pulling a jack or a heart from the deck? Okay, so we know that there's 52 cards total for him to pick from, so that's our denominator. Now we need to figure out how many cards will satisfy the requirement. Okay, so first option, he's happy with a jack. So there's 4 jacks that are good for him. Okay, however, he would also be happy by getting a heart. So there's 13 hearts to choose from. So 13 out of the 52 are good. but we double counted one of the cards. So I said that any of the 4 jacks is good. But then I also said any of the 13 hearts is good. So we notice that the jack of hearts got counted twice, but there's only 1 jack of hearts in the deck, so we shouldn't count it twice. So to account for this overlap, we need to subtract the intersection. So since 1 out of the 52 cards gets counted twice, we need to subtract that away. Okay, so 4 plus 13 is 17, minus 1 is 16 out of 52, which reduces to 4 over 13, which is approximately 0.308. Okay, so again, if you don't believe you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, skip this, I already counted it, 15, 16. So only 16 out of the cards fit the requirements. Bella rolls a die. What is the probability she rolls an even number or a number that is less than 4? Okay, so let's list out the possibilities. These are the 6 outcomes on a die. So how many of them fit her requirements? Well, she can roll an even number, so 2, 4, and 6 are good, or a number that is less than 4. So 1 is less than 4, that's good. 2's also less than 4, but we already included it from evens. 3 is less than 4, and the rest of them aren't less than 4. So it looks like 5 out of the 6 are good. Okay, but let's do it using symbols also. Okay, so we're looking for the probability that she rolls an even number or less than 4. Okay, so she's happy if she rolls an even number or if she rolls a number less than 4. But then we can't double count. We can't include the numbers that are both even and less than 4. Oops. Should have been the intersection symbol, the upside down U, because we don't want to include the numbers that are both even and less than 4. Okay, and then this symbol we could say is the union symbol. We're looking for the combination. It can either be even or less than 4 or both. Any of those make Bella happy. Okay, so probability of even, well, earlier we said that's 2, 4, or 6. So 1, 2, 3 out of the 6 die rolls fit the even requirement. Okay, but she's also happy if she gets less than a 4. So 1, 2, and 3. 3 numbers are less than 4. Okay, but if we just forgot about this and we added these together, we get 6 out of 6, meaning it's guaranteed to happen. But we know that can't be. We know there's a possibility that she doesn't win. So we need to get rid of the possibility where both of these happened. Okay, so how many numbers are both even and less than 4? Well, that's just 2. 4 does not count because 4 is even, but it's not less than 4, it's equal. So 1 out of the 6 numbers is both even and less than 4. So simplifying, 3, 6 plus 3, 6 is 6, 6, minus 1, 6 is 5, 6.